Hello friends, I welcome you in lecture number 43 on Laplace transform. In this lecture we are going to discuss two formulas for inverse Laplace transform using convolution theorem. We are familiar with the formulas of inverse Laplace transform of s divided by s square plus a square and inverse Laplace transform of 1 divided by s square plus a square. We know that inverse Laplace transform of s divided by s square plus a square is cos 80 and L inverse of 1 divided by s square plus a square is sin 80 divided by a. Now suppose instead of s square plus a square we have square of s square plus a square in the denominator, then how to find out inverse Laplace transform? So we are going to develop formulas for inverse Laplace transforms of s divided by square of s square plus a square and 1 divided by square of s square plus a square using convolution theorem. So using convolution theorem we will prove these two formulas. Inverse Laplace transform of s divided by square of s square plus a square is given by t sin 80 divided by 2a. And inverse Laplace transform of 1 divided by square of s square plus a square is given by sin 80 minus 80 cos 80 divided by 2 times a cube. In some examples we will require these two formulas for finding inverse Laplace transform. So we will remember these two formulas also. So first we derive inverse Laplace transform for s divided by s square plus a square square and we will use convolution theorem. To use convolution theorem, first we have to write our function as a product of two functions whose inverse Laplace transform can be obtained by the methods which we have discussed so far. So this I write as s divided by s square plus a square into 1 divided by s square plus a square. I split this square into s square plus a square into s square plus a square and I keep one s with s square plus a square and I write 1 upon s square plus a square in the product, and I will consider one function as capital F of s, another function as capital G of s. So suppose this is equal to capital F of s into capital G of s, where f of s is equal to s divided by s square plus a square and G of s equals 1 divided by s square plus a square. And then we have to write the formulas for inverse Laplace transforms of capital F and capital G. L inverse of capital F of s equal to L inverse of s divided by s square plus a square, and we know the formula for this, it is cos 80, and this is equal to small f. Inverse Laplace transform of capital F is denoted by small f. Similarly, we write inverse Laplace transform of capital G. Capital G is 1 divided by s square plus a square, and inverse Laplace transform of 1 divided by s square plus a square is sin 80 divided by a, and this we denote by small g. Now once we have inverse Laplace transform of capital F and capital G, we can apply convolution theorem to find out inverse Laplace transform of the product of f and g. By convolution theorem, now inverse Laplace transform of product of f and g, that is inverse Laplace transform of capital F into capital G, equal to convolution of small f and small g. And by the definition of convolution, this is equal to integral from 0 to t f of u g of t minus u, integral is with respect to u. and then we substitute values of f of u and g of t minus u. F of t is cos at, therefore f of u is cos au. I substitute f of u equal to cos au into value of g at t minus u. So here we replace t by t minus u. G of t minus u will be equal to sine of a into t minus u divided by a. Sine of a into t minus u divided by a. Integral is with respect to u. Now to integrate this, we will apply the formula for 2 cos alpha into sine beta, 2cs, that is equal to sine of alpha plus beta minus sine of alpha minus beta. So we can remember this formula as 2cs equal to s minus s, and we have to adjust these two also, and this 1 by a is independent of u, that we can take outside. So we rewrite this as, first we rewrite in this way, 2 cos au into we multiply t minus u by a, so that we have sine of at minus au. Integral is with respect to u. Now we apply this formula with alpha equal to a into u and beta equal to a into t minus a into u. This is equal to 1 by 2a integral from 0 to 2. First we have to add alpha and beta, that is a into u plus at minus au. So if we add these two, we can see a into u will cancel out and we are left with sine at minus sine of subtraction of these two angles, that is a into u minus at minus au. This is equal to a into u minus at plus a into u, that is a into u plus a into u is 2 into au minus at. So that I write directly here, 2 times a into u minus at. So we have rewritten our function using the formula of 2cs equal to s minus s. Now we can integrate with respect to u, and be careful, variable of integration is u, therefore t is constant and therefore sine at is also constant. So here we have this type of situation, integral of sine at with respect to u. Sine at is constant, so we can take it outside integral and into integral of 1 with respect to u. Therefore integral is sine at times u, that I write in this way, u times sine at, because t is considered as constant. And here integral of sine 2au minus at, integral of sine is minus cos, therefore negative negative will be positive, and here we write cosine of 2au minus at divided by coefficient of u, which is 2a. So here I must divide by 2a. Limits of integral are from u equal to 0 to u equal to t. Now we substitute upper limit and lower limit. Let me remove this now. Upper limit is u equal to t. So first we put u equal to t everywhere in this. So if we take u equal to t, we have t sine at plus, if we take u equal to t here, we will have 2at minus at. 2at minus at is cos at. So we have cos at divided by 2a. This is for u equal to t, that is for upper limit. And for lower limit we have to substitute u equal to 0. So this term will become 0, and if we put u equal to 0 here, we will have cosine of minus at, but cos function is even function, so I can directly write cos of minus at equal to cos 80. Here I am using the fact that cos is even function. If I take u equal to 0, I will have cosine of minus 80, that I write as cos 80 because cos is even function. And now we can see here we will have minus cos 80 divided by 2a. This is plus cos 80 divided by 2a. So they will cancel each other and we are left with t sin 80 divided by 2a. Therefore, we have shown that inverse Laplace transform of s divided by square of s square plus a square is equal to t sin 80 divided by 2a. And we will remember this formula. Sometimes we will need this formula to obtain inverse Laplace transform of those functions which can be written in this form. So it is very easy to prove this formula. We are just using convolution theorem by considering given function as a product of two functions, and then using convolution theorem we find that inverse Laplace transform of f into g is nothing but convolution of f into g, and then after this step it is problem of integration. Now we try to prove this second formula. In second part we have 1 divided by square of s square plus a square. So this also I write as product of 1 by s square plus a square with itself. Here f and g both are same functions, f of s into g of s, where capital F of s equal to 1 divided by s square plus a square, and this is equal to g of s also, and L inverse of 1 by s square plus a square is sin 80 divided by a. So this is our small f and both are equal, small g. Now we apply convolution theorem for inverse Laplace transform. By the convolution theorem, now by convolution theorem, inverse Laplace transform of capital F of s into capital G of s equal to convolution of small f and small g. This is equal to, by the definition of convolution, 0 to t f of u g of t minus u integral with respect to u. F and g are same, sin 80 by a. Therefore f of u is sin au divided by a. First we write f of u, it is sin a into u divided by a, and g of t is also sin 80. Therefore g of t minus u will be equal to sin of a times t minus u. G of t is sin 80 by a. We are interested in g of t minus u, so here we replace t by t minus u, and we have sin of a into t minus u divided by a. Integral is with respect to u. Here also we have to use the formula. We know that 2 times cos alpha into cos beta, this is sin alpha, 2 times sin alpha into sin beta. This is going to be, let me recall this. Okay, fine. So here we have negative sign minus 2ss. This is going to be cosine of alpha plus beta minus cosine of alpha minus beta. We have 4 formulas like this. 2sc equal to s plus s, 2cs equal to s minus s, 2cc equal to c plus c, and minus 2ss equal to c minus c. So here we are going to use this formula, minus 2ss equal to c minus c, that is minus 2 times sin alpha sin beta equal to cosine of alpha plus beta minus cosine of alpha minus beta. So we can multiply by minus 1/2 and we can divide by minus 1/2, and this a into a, that is a square, is constant, so that also we can take outside integral. So minus 1/2 integral from 0 to 2 times sine of, I write this first, sine of at minus au into sine au integral with respect to u, and here we have minus 2. So I multiply and divide by minus 2. I consider this 1 by a square outside integral because it is constant. I rewrite sine of a into t minus u as sine at minus sine of at minus au into sine au integral with respect to u, and now I apply this formula with alpha equal to at minus au and beta equal to a into u. So in the next step we apply this formula. This is minus 1 by 2 a square integral from 0 to 2 cosine of addition of these two angles at minus au plus au, that is au will cancel out and we are left with cos at minus cosine of at minus au minus au, that is going to be minus 2 au, that I can rewrite as minus 2 au plus at, integral is with respect to u. Again I repeat, first I add at minus au with au will cancel out and we are left with cos at, and then we subtract this a into u from at minus au. So we will have at minus 2 au, that I rewrite as minus 2 au plus at. Here my variable of integration is u. Now we integrate with respect to u. So as in the earlier case, here also cos at is constant. So cos at is constant and integral of du is u, minus integral of cos is sine function. So here we rewrite this as sine of at minus 2 au, and we have to divide by coefficient of u, which is minus 2a, and limits of integral are from u equal to 0 to u equal to t. Again we repeat, cos at is constant because integral is with respect to u. So we write cos at as it is, integral of du is u, minus integral of cosine function is sine function, so sine of this angle divided by coefficient of u, which is minus 2a, that I have written in the denominator. Now I substitute limits of u. First I put u equal to t. So first we write for u equal to t. If I take u equal to t, I will have t times cos at. This negative positive, in the denominator we have 2a. We put u equal to t, that is sine at minus 2at. At minus 2at is sine of minus at. This is for u equal to t, minus we take u equal to 0. So because u is in the product, this term will be 0, and if we take u equal to 0 here, we will have sine at and this negative positive, so plus sine at divided by 2a. For u equal to 0, this is going to be sine at minus 0. Now we simplify this, minus 1 by 2 a square. Here we have t cos at as it is. Now here sine of minus at is minus of sine at. Sine is odd function, so negative sign will come out. divided by 2a, and this is minus sin 80 divided by 2a. Again we simplify this. This is equal to minus 1 by 2a square t cos 80 minus 2 times sin 80 divided by a, that is 2 will cancel out. And now here we take LCM as a, so we have minus 1 by 2a square. Here I consider a, I will have 80 into cos 80, I have to multiply this by a, minus sin 80. Again we can take this negative sign in the product of this, and we can combine these two, 2a square into a, that is 2a cube, and if I multiply this by minus 1, I will have sin 80 minus 80 cos 80 divided by 2a cube, and this is inverse Laplace transform of 1 divided by square of s square plus a square. So remember this formula also, it will be helpful sometimes in finding inverse Laplace transform of a function which we can write in this form. So in this lecture we have obtained formulas for inverse Laplace transform of two functions, and for that we have used convolution theorem. So we can see we have proved these two things. Inverse Laplace transform of s divided by s square plus a square square is t sin 80 divided by 2a. Inverse Laplace transform of 1 divided by square of s square plus a square is sin 80 minus 80 cos 80 divided by 2a cube, and you can see we obtain the same answer which we are asked to prove, sin 80 minus 80 cos 80 divided by 2a cube. Okay, fine. So I stop here. We have seen enough examples of convolution theorem for obtaining Laplace transform as well as inverse Laplace transform. So now you must be able to obtain the inverse Laplace transform using convolution theorem. If you have any doubts related to this, you can ask in the comment section.